This is an introduction to exercise 5I on exponential growth and decay on page 243 of your textbook. Now, essentially, what this exercise comes down to content-wise is the one formula applied in different ways. And there are three main ways it's applied. We're going to focus on those three and see how we go from there. In the general form, this is what we're more familiar with. We've got this formula right here. And for those of you that have done general or further, it might seem familiar. A equals to A0. Does anyone know what A0 stands for?
Initial.
Yeah, the amount you start off with. Those of you that have done financial maths, it's like the principal, how much you start off with. A0 times e to the power of k times t. Now t, we're assuming could be time, right? Could be in years, could be whatever it is. We just follow the formula as we see fit. And k is just a constant. It's just a constant, and typically that indicates the rate. So for example, if it's a 7% increase per year, you guys know that's 0.07. And k would be 0.07 in that situation. Okay. The three contexts we're going to use, we're going to apply that is for cell growth, radioactive decay, and then I've got an example over here on population down here. Okay. But we'll focus on cell growth first. It's a very unique formula, but hopefully those of you that have done biology or do biology will be able to relate the understanding there. So in this case, we're supposing a particular type of bacteria cell divides into new cells. So from 1 divides into 2 every td minutes. Let n0, that one right there, be the initial number of cells. Of course, it's always initial for n0. And t, this value of t right there, is just the number of time in minutes. Okay, so td is how long it takes to split, or in other words, generation time, for those of you that fancy bio. N0 is the initial number of cells. Lowercase t is the time. And of course, capital N will just be the actual number of cells at that time. Any questions? Okay, let's put this into practice. I'm going to write that formula up here just so we are clear. N equals to N0 times 2 to the power of t over td. Okay, so what is the generation time of a bacterial population that increases from 5,000 to 100,000 cells in 4 hours for growth? So what information am I looking for? What's the variable? TD, good, thank you very much, equals the question mark. What information do I have? I know it starts from 5,000, so I know N0 equals to 5,000. I also know that T, lowercase t, is 4 hours. And I know that capital N, so the number of cells, is 100,000. Any questions about that? Yes?
Would you convert T into minutes?
Thank you very much. I'm going to do it later, but I was going to do one of those, oh, what have I done wrong? But thank you very much. That is right. 4 hours, we have to convert into minutes to make sure that we've got it consistent with that formula. So that is 4 times 60, which gives us 240. Okay. Let's sub that into our formula. So subbing this in, that's not how I meant to do that. There we go. Subbing that in, we get N, which is 100,000, equals to 5,000, times by 2 to the power of lowercase t, which is 240 in this case, over TD. There we go, TD. From this stage, this will be a calculator question, or it could be. I'm going to rearrange it to get TD first, and then we'll put it in the calculator. So we get 20 over here. 10,000. Yeah, 20 equals to 2 to the power of 240 over TD. In which case I could go log base 2 of 20 equals to 240 over TD. Are we okay with that? Following along with that? Lovely. And then multiply both sides by TD divided by blah, blah, blah. You guys know this stuff. So TD equals to 240 over log base 2 of 20. If you would like to put this in the calculator, this is a very standard no calculator question, but of course I'm not expecting you guys to go beyond that point if you are without a calculator. With the calculator, of course, 240 divided by log base 2 of 20 gives us an answer of 55.53. 5.53. That's it? Units? TD is generation time, right? And what is time measured in? Minutes. Okay? In minutes, because that's what we've said over here. Every TD minutes. Sweet. Any questions? Okay, I know it's a very weird concept, but let's try to apply that concept later on in the exercise questions. I want you to refresh your brain back to the original formula. We're going to do radioactive decay. So radioactive decay is something that we use to try and figure out how old something is, right? For example, there's really, really old fossils or rocks or whatever it is that people are interested in. We can look at how radioactive a certain material is and figure out its half-life, okay? So in this situation, we're going to be using this formula here. Except, of course, it'd be very unrealistic to try and convert 50,000 years into minutes, right? So we're going to keep it as, there it is, time in years. Okay, time is in years. A0 is the initial amount. K is the positive constant that stays the same, and we're going to refer back to this formula in a moment later. Okay, so let's look at this question here and try and determine the answer. Let's move that to the side. Okay, all right. So after 1,000 years, so automatically T equals to 1,000. Do I have to change to minutes? No, good. Sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life of radium-226. Now, we're going to use a formula, and then to find the half-life, we're going to be using this formula later. Okay? But let's start with using the exponential equation. T equals to 1,000. What other information do I know? I know that A, right, the amount that we have left, is only 64.7% of A0. So how much we have left is only 64.7% of what we had to begin with. Is that fair? Of course, I don't write 64.7%. What do I write? Thank you very much. 0.647. So A equals to 0.647 A0. So let's put that in the formula. Of course, our formula is A. So that's, there we go, 0.647 A0 equals to, again using the formula, that's A0, there we go, times e to the power of kt. Of course, t is 1,000. Oh, sorry, negative k, you're right, it is a decay, my apologies. Negative k, as it says in the formula right there, and then times by 1,000. Of course, simplification-wise, I can just cancel, and we end up with 0.647 equals to e to the power of negative 1,000 k. And then from there, of course, we can rearrange this value, and we get log base e of 0.647 equals to negative 1,000 k, which therefore k equals 2, and I'm going to put it straight into the calculator. I'm going to say negative, we're going to say negative log base e, where is that, ln, there it is, log base e of 0.647, and then we're going to divide that by 1,000, which gives us an answer of, I've done something wrong.
It's negative 1,000.
Yeah, but I put the negative up here. I've done something wrong. What have I done wrong? No, that sounds alright actually. My apologies. So it actually ends up being 4.35 times 10 to the power of negative 4. Oops. There we go. Which is the same as k equals to 0.000435. Okay. I know it's really gross, but we're going to use that now. Okay? So now we're going to go back to this formula here, where A equals to half of A0. So then I can say, because A equals to half of A0, A equals to, A0, e to the power of negative kt equals to half A0. So I've just substituted in this formula. Instead of writing A, I've written half A0 and the rest of the formula, because we know the value of K. Rearranging that, I'm going to skip a couple of steps and say we get to T equals to log base E of a half over k, which when you put it in the calculator gives you 1591.95. So approximately 1592 years. I'm going to skip the steps of rearranging because I'm assuming you guys are not able to do that anyway. Any questions about that one? It's very weird, I know. Just make sure that you use the values given to you. You change any percentages and decimals and use the right units. You substitute that into the formula, and once you've done that to find the value of k, you use this formula to determine the half-life. Because k isn't half-life, k is the rate. Okay, last one is actually the simplest one in my opinion. We're trying to find the population of a town. So population of town was 8,000 at the beginning of 2007 and 15,000 at the end of 2014. And we have to assume the growth is exponential. Find the population at the end of 2016. So let's use the formula. So in this situation, I'm going to define P as population. I'm going to say P equals to, how much did we start off with? 8,000. Good, 8,000. Now, here's the tricky part, right? 8,000 times e to the power of k, because it's increasing. Remember, if it's a growth, then it's a positive k value. If it's a decay, it's a negative k value. What is the time? Years. It is in years, but what is the value of time? That's so deep. What is the value of time? So from 2007, 2014, you'd go 2007, 2008, 2009, 10, 11, 12, 13, 14. What's the problem with that? Thank you. That's the trick. Honestly, it's a trick question. I'm not going to lie. The beginning of 2007 to the end of 2014. So it's actually 8 years. So 8k. Rearrange to get, P needs to be replaced, of course, because we know the population at the end of 2014. So it's 15,000. So rearrange that to get, where's it working? There we go. To get k by itself, I'm going to divide both sides by that. We get 15 over 8 equals to e to the power of 8k. Apologies. And then rearranging, I get log base e of 15 over 8 equals to 8k. And divide both sides by 8, I get k equals to ln 15 over 8 over 8 again. Which actually ends up being approximately 0.079. Are we done with part A? Because k is the value of what? What is that? What does k tell us? The rate. Good, the rate. But we're not finding the rate, we're finding the population at the end of 2016. So to do that, all we're doing is, we're saying, okay, well, if we've got a approximately 7.9% increase, we can apply that into the formula and say, okay, well, 2016, that's the end of 2016, so that's 2 more years on top of 2014, so let t equals to 10. And we use the formula, we say, okay, well, it's A, or P in this case, sorry, P equals to 8,000 times by e to the power of 0.079 times by 10. And then you solve that to get P. I'm not going to go through that one because I'm assuming you guys know how to substitute values in. But in the next part, it says, in what year will the population be double that of 2014? How would I approach that question? Yeah. Good. Correct. We'd let the value of P be 30,000, double that of 15,000, and then we'd use that to rearrange and solve for the value of T. Any questions? Okay.